This lesson shows you how to set up problem 6 in the Newton's Laws free body diagram homework assignment. In this problem, we have a crate that is sitting on a surface, and the crate has a weight of, 1,500 newtons. And in part A, it's being pushed by a force, F, at an angle of 20 degrees from the horizontal, like that, 20 degrees above the horizontal. The magnitude of that push is given as about 230 newtons. And we're told that the box is being pushed at a constant speed, and asked to find the force or the coefficient of friction between the box and the floor. All right, well, we do this problem starting out like we do all of the problems. You draw a free body diagram after you've sketched the situation. Here is our box. We have the force of gravity acting down on it, which is 1,500 newtons. That's mg. We have the normal force of the ground onto the box. We have the force of the push, which is at an angle of 20 degrees and has a magnitude of 230 newtons. And finally, we have friction, which opposes the motion. Since the box is going to the right, then friction will be pushing back to the left. Now, after you have drawn your free body diagram, you need to pick a coordinate system and resolve all of the vectors, all of the different forces, into their x and y components. So we'll pick horizontal to be the positive x direction to the right, and up to be the positive y direction. The normal force and gravity have only a y component. The force of friction has only an x component. So the only thing that we need to resolve into x and y components would be the 230 Newton push. Its y component will be it'll be the negative y direction. The x component is that it is in the positive x direction. Okay. So since the 20-degree angle is right here, the x component is adjacent, the y component is opposite. That means we'll use cosine for the x and sine for the y. We have the x component of the push is equal to 20 degrees times the cosine, excuse me, that would be 230 newtons times the cosine of 20, and FPY will be 230 times the sine of 20. The y one is in the negative y direction, so we'll need to keep that in mind when we do the sum of the forces. Okay, and now that we've resolved all of the forces into their x and y components, we need to apply Newton's second law. Sum of the forces in the x direction is MAX. Sum of the forces in the y direction equals MAY. The forces in the x direction all go on the left side here. Forces that are in the x direction, we have the x component of the push. In the positive x direction, and we have friction in the negative x direction. That's equal to the mass of the box times the acceleration of the box in the x direction. But because it's at a constant speed, then by definition there is no acceleration. So that side of the equation is equal to 0. In other words, the force of friction must be equal to Fpx. The force of friction is always equal to the coefficient of friction times the normal force. Fpx in this case is 230 newtons times the cosine of 20. Since the goal here is to find the coefficient of friction, I need to find the normal force. And since it's in the y direction, we'll probably have some success using the y version of Newton's second law. Let's put all of the forces that have a y component, let's put the y component on the left side of this equation. We have the normal force in the positive y. We have the 1,500 newtons of gravity in the negative y, so we'll subtract. We also have, in the negative direction, the y component of the push, so that's 230 newtons times the sine of 20 degrees. That must equal the mass of the crate times the acceleration of the crate in the y direction, but once again, the acceleration is 0. The box is not accelerating, it's moving at a constant speed. Okay, so you can solve this equation for the normal force, and once you've done that, you'll plug in the value that you get for the normal force, plug it in over here, and then all you have in that equation is numbers and the coefficient of friction, which is what you're looking for. So at this point, it's algebra. Just solving for Fn, then solve for mu. Okay, now how is this going to change in Part B? In Part B, we are to assume that the coefficient of friction is the same as what you found in Part A. So this time we'll take the coefficient of friction as a given, the one that you solved for in Part A. But what's going to happen is that now, instead of pushing down on the box, we've decided to maybe tie a rope to it and pull on the box. So we're going to have the pull this way, still at an angle of 20 degrees. And we no longer have the push down. So we'll get rid of that force in our free body diagram. But everything else in the free body diagram stays the same. So we can move on to resolving all of the forces into their x and y components. Well, the only force that has both an x and a y component is the 230 Newton pull. So once again, we need that Fpx is 230 newtons times the cosine of 20. And Fpy is 230 newtons times the sine of 20, but this time the y component is up in the positive y direction. Okay, so now let's make that the positive y direction. The other thing that changes is now that we're pulling instead of pushing, there's not going to be as much frictional force, so the crate will start accelerating. So when you apply Newton's second law in the x direction, you won't have an acceleration of 0 anymore. So let's get rid of that 0 and replace it with the mass of the crate times the acceleration of the crate in the x direction. And that's what you're looking for, the acceleration of the crate in the x direction. So this part we'll need to do over, because that other part was dependent upon the acceleration being 0. So Fpx, we know from earlier, is 230 times the cosine of 20. Friction is still the coefficient of friction times the normal force, so you should plug in the value for coefficient of friction that you got in part A. And once again, we need to know the normal force. Now, the normal force is not going to be the same thing that it was in A, because in part A, we were pushing down, and in part B, we're pulling up. So let's look carefully. Let's look carefully at the sum of the forces in the y direction and see how much of this can we use from what we did before. The normal force is still up. The force of gravity is still down, so that stays the same. What's different is the y component of the pull. It was down in part A, but now it's up, so I need to make that positive. You can then solve this equation for the normal force, plug in the value you get for the normal force there into F sub n. You already know mu because you found it in part A. The mass of the box you get because we know that the weight of the box, 1,500 newtons, is equal to the mass of the box times gravity. So to get the mass of the box, you need to divide the 1,500 newtons by 9.8. At that point, everything in this equation is a number except for the acceleration, so you can solve for that.